Now I'd like to take a look at a problem that is not in your textbook, but this is one that you can really sink your teeth into. This one comes from a textbook that was written by a man named Searway at James Madison University. Here's the example. It involves the arm. A 5-kilogram weight is held in the hand with the forearm in the horizontal position as shown in the figure. The biceps muscle is attached 3 centimeters from the joint, and the weight is 35 centimeters from the joint. The biceps makes an angle of 15 degrees with the vertical. Find the upward force that the biceps exerts on the forearm, which is made of the radius and ulna, and the downward force on the upward arm, which is the humerus, acting at the joint. Neglect the weight of the forearm. Wow! We're going to apply the conditions of equilibrium to solve this problem. We need to first sketch kind of a simplified diagram so we can see where the forces are acting and on what exactly they're acting. Here is my forearm, which is made of the radius and the ulna. Here's the weight that's being held in the forearm, and the earth pulls that weight downward. Here are the biceps. The biceps are acting upward, and I'm going to call that force that's exerted by the biceps muscle FB, and they're telling us that the angle that's there is 15 degrees. And now we need the humerus, and you can see in this diagram of the situation that the humerus is not exactly vertical, it's a little bit horizontal, and so I'm going to show that as a little horizontal force, and I'm going to call that F with a subscript H for the force that's exerted by the humerus on the elbow joint. Now what? Well, I have to figure out what the conditions for equilibrium are. There are two. One of them is translational. The net force acting on the forearm weight system is equal to 0, and this breaks into two equations. There is an x equation, the forces in the x direction are equal to 0, and the forces in the y direction add up to 0. The other equilibrium condition is rotational. So I have to figure out the net torque about some pivot point is equal to 0. And the logical place to take the pivot point is at the elbow joint. So I'm going to call that my pivot point right there. So that clockwise torques about that pivot point have to be countered by counterclockwise torques. And those have to be equal to 0 as well. Now, let's break these forces into horizontal and vertical components. I have an FH, and I have an FB, and I have an FW. I'm going to resketch the diagram with these forces shown in their component form. So, here are the forces sketched with distances shown as well. I have a downward force and a sideways force from the humerus, FH. I have an upward force and a sideways force from the biceps muscle, that's FB. And I have just a vertical downward force from the weight, which is FW. So now what? Well, now I want to write each of these conditions of equilibrium and figure out what we get. The first condition of equilibrium says the forces in the x direction are equal to 0. Well, what do I have? FHX in the positive x direction, I'm going to call to the right positive, minus FBX, and that's got to be equal to 0. So that tells me that whatever force is acting on the humerus in the x direction has got to be equal in magnitude to the x component of the force that's acting on the biceps. That's my first relationship. Now what about the y forces? Well, the y forces, the net force in the y direction is equal to 0. I have two downward forces and I have one upward force. Let's call up positive. So the force on the biceps in the y direction minus the force on the humerus in the y direction minus the weight has got to be equal to 0. And so there is another relationship that we have. And since we know what the mass of the object is, since the weight of the object is 50 newtons because its mass is 5 kilograms, I know a number for FW, and that may help me in figuring out what these other numbers are. Now lastly, I've got to talk about the torques. The net torque has got to be equal to 0. Well, what is the torque about the pivot point? There are 1, 2, 3, 4, 5 components of force that are acting on this moment arm. But the humerus components have no moment arm because they're acting at the pivot point. The X component of the biceps muscle doesn't cause rotation because it acts parallel to the moment arm. The only two things that can cause rotation are the Y component of the biceps force and the weight. The weight tends to cause clockwise rotation. The biceps tends to cause counterclockwise rotation. So I'm going to say that the torque due to the biceps minus the torque due to the weight has got to be equal to 0. Well, what is the torque? If we call this distance between the biceps and the pivot point RB for the distance of the biceps, and let's call the distance from the pivot point to the weight RW, then I could write these torques. The torques due to the biceps are RB times FBY minus the torque due to the weight is RW times FW, and that's got to be equal to 0. But now what is FBY? FBY comes from this force triangle up here. FBY is going to be FB times the cosine of 15 degrees. So I'm going to say RB times FB times the cosine of 15 degrees minus RW times FW is equal to 0. And now I know everything in that equation except FB, and I can solve that equation for FB. Once I know that, I can figure out what FH is, and that's how I'm going to solve this problem. If you'll permit me, I'll solve for FB in a single step, and now I'll put in the numbers. I find that the force on the biceps is 604 roughly newtons. What about the force on the humerus? I can relate that to this X component there and this Y component right there. I know that the force on the humerus is going to be the square root of the force on the humerus in the X direction squared plus the force on the humerus in the Y direction squared. So if I could get numbers for FHX and FHY, then I could put those things together to figure out what FH is. Let's start with the X component. And I know that the force on the biceps in the X direction is going to be FB times the sine of 15 degrees. I can say that FHX is going to be FB X, which is FB times the sine of 15 degrees, which is 603.9 newtons times the sine of 15, and now I'll put that into my calculator to get some result. The X component that's exerted by the humerus is 156 roughly newtons. What about the Y component? I can solve this Y equation for the Y component. FBY minus FW is going to be equal to FHY. So now FBY we figured out is FB times the cosine of 15 degrees. And we know the weight is 50 newtons. So FB times the cosine of 15 degrees minus FW, let me put in the numbers. I get that the Y component acting on the humerus is a little more than 530 newtons. What is the whole humerus force? It's this square root of the X component squared plus the Y component squared. So now let's feed in the numbers. I get that the force on the humerus is 556 newtons. So that answers the question. The biceps is pulling up at 604 newtons. The humerus is pushing down at 556. Though there are some angles that are involved there, we didn't calculate the humerus angle. We could using the X and the Y components of the humerus force. I haven't bothered to do that in this problem. So briefly, let's summarize. We have defined torque. We've talked about clockwise torques and counterclockwise torques. We've written the torque formula, R cross F, and we've applied it to some numerical problems.